We're looking at proof. One of the styles of proof we saw last year was induction. So let's look at it a bit further. We saw the series type. That's where we started with induction. So it's something like this. Prove that the sum of, well, there's the general term, is equal to this expression there. So the first thing we did was prove it true for the first case. First case in this case would be r equals 1. Well, I've called it n equals 1. But 4 over 1 times 2 times 3, we get 2/3. Sub it into the formula on the right-hand side, and we get 2/3 as well. So yeah, left-hand side is equal to the right-hand side, so we know it's true for the first case. Now, when I write my assumption down, I can start using symbolic notation. So assume the result's true for n equals k, where k is a positive integer. So there is my assumption. We're going to prove it for the next case. So that's what we're trying to prove. Okay, let's do a proof. So in our series type, we split it out. We take the k plus 1th term out of the sum. That allows us to substitute in our assumption, and we've got an algebraic fraction to play with. Now, looking at what we were trying to prove, it would be stupid to put the 1 into the algebraic fraction because we're going to have to get it out of it again anyway. So we've got the 1, we'll leave it there. We just got to be careful because we want minus. So when I put it all into one fraction, this 4 becomes negative 4 because we're saying minus the fraction. You've got to be careful with that. We've got our common denominator there. Oh, I was going to say the k plus 3 cancels, but it doesn't, of course, because I've got that minus 4. Let's tidy that up then. It's the k plus 1 that ends up cancelling once we do all that. And that, I think, is what we wanted, isn't it? Now, what you have to remember is, even though we're calling it deduction, it's still a direct proof. So, because it's deductive, it's direct, we conclude with an if-then statement. That's why we write this down. Now, I've sort of written the if-then backwards. So when I've done, I always say, hence the result is true for n equals k plus 1, if it is also true for n equals k. But if we were really going to do an if-then statement, I suppose there's nothing wrong with saying, if it's true for n equals k, then it is true for k plus 1. There's your if-then statement. So I've just written it a different way. And once we've done that, we tie it all together. So finally, we've got to induce the solution. We pull the first thing we did, where we proved it for the first case, and then we pull it into our proof and use it. So we said, okay, we showed it was true for n equals 1. So we can now induce the solution using the fact that it's true for n equals k plus 1 if it's true for k. So it must be true for all integers by induction. Well, all positive integers by induction. In this case, I suppose I have to have positive integers because the question did say prove it true for positive integers. There's a little variation. Instead of adding the terms together, multiply the terms together. So it's going back a few years now that this one appeared. And also notice the first term is not 1, it's 3. So you've got to be careful with that. So we prove it true for n equals 3. So the first term, 1 minus 2/3, that'll be a third. Right-hand side, the formula gives us a third as well. So yep, good. But it's true for n equals 3. So easy just to write down n equals 1 because out of habit it's always n equals 1 and so on. Okay, my assumption. Now this time when I write my assumption down, I'm assuming k is an integer such that k is greater than or equal to 3. We might use that fact that k is bigger than or equal to 3 in our proof. So we include it in our assumption. So there's our assumption. We want to prove for the next case. So that's what we're trying to prove. Same idea, but this time I'm separating out the k plus 1th term, but it's multiplied rather than added. So you see how I've now rewritten the multiplication with the second last term there to make it obvious, hey, I'm going to sub in my assumption into this. So that's what we've got. 2 on k plus 1 times 1 minus 2 on k plus 1. In this case, I am going to have to combine that all into one fraction. And k plus 1 minus 2 is k minus 1. We now have some cancelling. The k minus 1, yeah, and that'll do us. So there's our 2 on k plus 1. Hence, etc., etc., etc. Then the next type we looked at was the divisibility type. Something like this. Prove that n squared plus 2n is a multiple of 8 if n is even. So a little bit different here. We're not just talking about consecutive numbers. We're dealing with even numbers. First even number is 2. So let's sub it in and we get 8. And last time I checked, 8 is a multiple of 8. So yep, works for n equals 2. Now my assumption, true for n equals k, but k is going to be an even number. So in other words, k squared plus 2k is 8p, where p will be some integer, but the other thing we know is k is even. Prove it for the next even number. So not k plus 1 this time, k plus 2. That's what we're trying to prove. Okay. Expand it all out. I've got 8p plus 4k plus 8. Remember, I'm trying to pull 8 out as a common factor. So when I do that, I get k on 2. Now ordinarily that's a problem because I want to say that that is an integer. That's why in my assumption, making k being even, we're okay. Because we know any even number divided by 2 is an integer. So actually stating k is even in my assumption is crucial for this proof. So I can say, well, q equals that, and because it's unusual with a k on 2, good to mention why we can say that's an integer. Right? Because k is even, I can say that. Hence the result's true, but this time for k plus 2. If it's true for k, and then since it's true for 2, it'll be true for all even numbers by induction. Could have done it a different way. Rather than going n equals k where k is an even number, I could have said while let n equal 2k where k is an integer. So now that also means n's an even number. So what would have happened there? There's my assumption, still a similar assumption, isn't it? 4k squared plus 4k is 8p. But then I'd be proving it for 2k. Next even number would be 2k plus 2. Okay, expand this out. And we're trying to get a common factor of 8 in all this. In this case, yes, 8 comes out quite nicely. And so we get p plus k plus 1, which would be an integer. So you might prefer to handle it that way. Hence it is true, etc., etc. We didn't really look at these ones last year. You're probably not going to see them in an extension 1 paper. Inequality type. But now we've been dealing with inequalities. Let's have a look at the induction. We're going to prove 2 to the power of n is greater than n squared, but this will only work for integers greater than 4. First case, therefore, is 5. Sub in 5, we get 2 to the power of 5 is 32. 5 squared is 25, and yep, 32 is bigger than 25. So that's fine. My assumption, n equals k, k is an integer, but it's also greater than 4. In other words, I'm saying 2 to the power of k is greater than k squared, and k is greater than 4. Prove the result is true for k plus 1. Now you'll notice I've used the technique of moving everything to the left-hand side. So rather than proving 2 to the power of k plus 1 is greater than k plus 1 squared, I'm going to prove that that expression is greater than 0. Got to get my assumption in there. My assumption was 2 to the power of k was greater than something. So I'll split my 2 to the power of k plus 1 into 2 times 2 to the power of k. So that expression won't be equal to, but it will be greater than 2k squared minus k squared minus 2k minus 1. Because we know the 2 to the power of k is greater than k squared. Well, that tidies up to be k squared minus 2k minus 1. Remember, we're trying to show this is always positive. Here's where I just use the other part of my assumption. Well, that's got to be bigger than 4 squared minus 2 times 4 minus 1. Because k is bigger than 4. And you might be saying, well, hang on, but you're subtracting something. How do you know it's going to stay bigger? Well, 2 times a number bigger than 4 will always be less than that number squared. Now, fair enough, if k was equal to, say, 2, I couldn't make that statement. They'd be equal, not greater than. But because we've said k is greater than 4, it is fair enough to make that statement. And that's 7, and 7's bigger than 0. So hence it's true for k plus 1, if it's true for k, and there we go. Since it's true for n equals 5, then it's true for all integers such that n is greater than 4 by induction. Here's a series type with an inequality. N equals 1 is our first case. So let's see what happens. Left-hand side we get 1, right-hand side we get 1. 1 is less than or equal to 1. Well, it's equal to, so therefore it is less than or equal to. So it is true. We're going to assume it's true for n equals k. K is a positive integer. So there's my assumption. We want to prove it true for the next case. So that's what I'm trying to prove. But notice again, I'm going to use the idea of, let's try and show everything in this case is less than or equal to 0. So I've moved the right-hand side across. Okay, let's have a look at this piece of algebra. What can we do? Well, let's get the assumption in there. So I split my sum. I'll pull out the k plus 1th term. There's the assumption 1 up to 1 on k squared, which we said was less than or equal to 2 minus 1 on k. Nicely, I've got a 2 minus 2 in there. That's good. What else can we do there? Well, I pull it all together into one fraction, I guess. So if we pull it all together in one fraction, let's play with the top. The top turns out to be negative 1. Remember, we're trying to show this whole thing's negative. Well, negative 1 is a negative number. K plus 1 squared must be a positive number. And we have assumed k is a positive number. So that fraction must be negative. So we can say that because we know k is greater than 0. Hence, the result's true for k plus 1 if it's true for k. Now we move on to just using the idea of induction. The things that are a little bit different. So look at this. We've got 2 vertical walls and the floor meet at a corner, as happens in most rooms. We can look at that corner. Oh, look at that. 2 walls and a floor. Okay. Then we wish to place cubes this way. So we stack them in the corner or along the edges of the wall. Let n be the number of cubes used to make the shape. We're going to use induction to show the number of exposed faces. So the number of faces that are open to the room, not up against a wall, not up against the floor, will always be 2n plus 1. Prove the result is true for n equals 1. In other words, 1 cube. I'm going to draw a diagram. There it is. We have 1 cube sitting in the corner. How many exposed faces can we see? Well, there's 3. What happens when we sub 1 into our formula? We get 3. So the formula works for 1 cube. Now I'm going to assume it's true for n equals k, where k is some positive integer. So in other words, I'm going to assume k cubes will always have 2k plus 1 exposed faces. We now want to prove it true for k plus 1 cubes. In other words, k plus 1 cubes will have 2k plus 3 exposed faces. Here's my proof, and again, I'm going to use a picture. So I'm going to add a cube to the pile that's already there. So what happens when I add a cube to the pile? The one I've shaded in there, that face will end up being covered up. It was an exposed face, but it will now become not an exposed face. So we know the addition of that cube will cover up one of the existing faces, but it will create another 3 exposed faces, because we'll end up with that. So there's the shaded one, it's now been covered up, but we now have 3 more faces. So the number of exposed faces for k plus 1 cubed must be the number of exposed faces we had for k cubes minus 1, 1 disappeared, plus 3. Well, we assumed it was 2k plus 1, so let's subtract 1 and add 3, and we get 2k plus 3. And that's what we were trying to prove. So it's still the same idea of induction, because now we're going to say, well, hence it's true for k plus 1 if it's true for k, and because we proved it true for 1 cube, it must be true for all cubes. All right, induction and recursive formulas. All right, so recursive formula, that's where, if you recall, we looked at it back in series and sequences, but that's where you get one term by using previous terms, and there's some formula that will link it out for you. If a recursive formula is defined with m preceding terms, so if it's made up of 4 terms, say, so it might be the previous 4 terms, 2 terms, whatever, then you'll need to prove true for the first m terms. So if the formula uses 1 term, you only need to prove it true for the first term. But if the formula uses the 2 previous terms, then you need to assume it's true for the first 2 terms, and so on and so on. And then you would assume it's true for k minus 1, however many you need, 1, 2, or 3. The recursive formula is always given to be true. You don't have to try and prove the recursive formula. They're telling you this is a fact, so you can use it in your proof. Okay, let's start with this one. The first term is the square root of 2. Every term after that will be the square root of 2 plus the previous term. We're going to prove that every single term in this pattern is less than 2. So in this case, my recursive formula only uses one previous term. So I only need to prove it true for the first case. Now they've told me that A1 is the square root of 2, and yes, that is less than 2. So all right, it's true for the first term. We assume it's true for n equals k, so I'm going to assume the kth term is less than 2. We now want to prove for k plus 1. So we want to prove the k plus 1th term is less than 2. Proof. Start with the recursive formula that they've given you, because that now allows you to get the assumption in. That's why you need as many assumptions as terms you're going to substitute in. So in this case, I only need k. So equals the square root of 2 plus k. So this must be less than the square root of 2 plus 2. Right? Because ak is less than 2. Well, 2 plus 2 is 4. And the square root of 4 is 2. So now if I read down, ak plus 1 is less than 2. And that's what we're trying to prove. Hence the result is true for k plus 1, etc., etc. Let's look at a more interesting one, the Fibonacci numbers. Remember the Fibonacci numbers? 1, 1, 2, 3, and so on. So there's the definition for the Fibonacci sequence. The first term and the second term are 1. And then we create every term by adding the 2 previous terms. So that's our formula. This is the beautiful thing about it if you recognize this number. Every term in the Fibonacci sequence is less than 1 plus root 5 on 2 to the power of n. 1 plus root 5 on 2 is the irrational number phi, the golden ratio. So that's why there's this connection between Fibonacci numbers and the golden ratio. Let's prove it, but now we have to prove it for the first 2 cases, because we're going to use 2 numbers when we sub in. So for n equals 1, we get, well, the first term is 1, and, well, the golden ratio is 1.6. Well, 2 I've rounded off. I think it's 1.619, something like that. So, yep, the first term works. What about the second term? The second term is also 1. Well, when I square 1.62, etc., I end up actually getting 2.62. So it still works. True for the first 2 cases. Now I have to make 2 assumptions, because I'm going to end up substituting in 2 terms. So I'm going to assume that term k is less than 1 plus root 5 on 2 to the power of k, and term k plus 1 is less than 1 plus root 5 on 2 to the power of k plus 1. We then want to prove true for k plus 2. Again, I've moved everything to the left. I'm going to try and show this is a negative number. Here's my proof. Start with the formula, and the formula was the 2 terms added together. So I've subbed in the 2 terms added together, ak plus 1 for ak plus 2. But then we also have this minus 1 plus root 5 on 2 to the power of k plus 1, and that's what we're trying to show is negative. We assumed those first 2 terms. The first one is less than the power of k, the second one to the power of k plus 1. Remember, we're trying to show this is negative. Nicely, each of these the bases, if you like, are the same. So I could factorise that. Let's pull out the lowest power, which is to the power of k. That, of course, is a positive number. 1 plus root 5 on 2 to the power of k would have to be positive. So what I'm left with now, I'm hoping, will end up being negative. Let's have a look at what I'm left with. That equals, when I get a common factor, 4 plus 2 times 1 plus root 5 minus 1 plus root 5 squared, which actually turns out to be 0. So whilst I was hoping for a negative number, 0 is fine as well, because remember we're just trying to show it's less than 0. And so, yep, that means it is less than 0. Hence, our result is true for k plus 2 if it's true for k and k plus 1. But because we know it's true for 1 and 2, then it must be true for 3, 4, and 5, and and so on. All right, the fun of induction.